Dear students, this is our 22nd lecture on organic reaction mechanism, and in this lecture we will be discussing methods of determining reaction mechanism. As you must have read in your undergraduate classes that organic reaction mechanism is a step-by-step description of a sequence of organic reactions through which the overall chemical changes occur for the conversion of a reactant into a product. Now, in case of reaction mechanism, we precisely know that what type of bonds are broken and what type of new bonds they are formed. In addition, the mechanism also tells us about the sequence or order of breaking and formation of these bonds. The reaction mechanism in addition gives us information about how many steps are involved in completion of that reaction, and also in case of each step, what is the relative rate of reaction for conversion of one kind of intermediate into another kind of intermediate before the formation of the product. And this mechanism of any organic reaction is usually determined by a few specific methods, and important among these methods they are product analysis, then second is study of intermediates, that is how intermediates they relate with the transition states or transition states they relate with the intermediates. Then third type of experiments, they are crossover experiments, they also tells us about the reaction mechanism. Fourth is isotopic labeling, is also used to formulate a organic reaction mechanism. And last is kinetic isotopic effects and other evidences in terms of kinetics and stereochemistry of these organic reactions. The mechanism of any reaction can be given by either any of this method or combination of one or more methods to prove the mechanism of that particular reaction. So we will discuss these methods one by one. First is product analysis, that how the mechanism of a reaction can be used to obtain an useful information for the reaction mechanism. So analysis of the product which is formed during the chemical reaction gives us a very appropriate for information about the mechanism of that reaction. And in product analysis we need to know the relative amount of products formed, because even a minor product formed which occurs as a competing reaction, that will provide an important information for determination of mechanism of that reaction. So we will discuss few problems which will prove that how important is this product analysis. For example, if you see this reaction here, alkanes, they are converted into hydroperoxides, and these hydroperoxides they are formed as major product in the auto-oxidation of these alkanes. Now this conversion of alkanes into alkyl hydroperoxide cannot take place in a single step. That is, it involves few steps. For example, we know that oxygen, there is a single electron on each oxygen because of the paramagnetic nature of this oxygen. And in the first step, this alkane will react with the oxygen, and H radical from the alkane is shifted to the oxygen, and hydroperoxide radical is formed as the intermediate, and this alkane will be converted into an alkyl radical. Then that alkyl radical will again react with another molecule of oxygen, and we will get this hydroalkoxy radical, and this alkoxy radical will react with another molecule of alkane, and H radical from here will be shifted to this alkoxy radical, and we will get alkyl hydroperoxides as the product. So from the analysis of the product formed in this reaction, we can tell that what are the different types of intermediates which are involved in reaction, and the mechanism involved is a free radical mechanism. Then second example is the hydrolysis of these isomeric allyl chlorides. If you see this allyl chloride here, this allyl chloride is a primary allyl chloride, whereas this allyl chloride is a tertiary allyl chloride, because here the chloride group is attached to a tertiary carbon atom, whereas here the chloride group is attached to a primary carbon atom. But when the reaction of these allyl chloride is done individually, even when this is reacted in presence of water as the nucleophile, then these allyl chlorides, they are converted into the allyl alcohols. But either when this is reacted with water as nucleophile, this will give us a mixture of primary and tertiary allyl alcohols. Either we use primary or tertiary, the formation of the products is same, and both the products, they are formed in the same quantity. That is, 15% of the product formed is primary, and 85% of the product formed is a tertiary product. Either we use primary reactant or tertiary reactant. So this proves that either this reactant or this reactant, when converted to give us these two products, means that a common intermediate is involved in these conversion reactions. So what happens is that this allyl chloride will give us this primary carbocation, whereas this tertiary allyl chloride will give us this tertiary carbocation. And we know that primary carbocation is less stable as compared to tertiary carbocation. So that is why this tertiary is formed from this primary carbocation, and the time taken for the formation of this conversion of this primary into this tertiary gives us the products which are formed. The tertiary product is formed in more amount because of the higher stability of this tertiary carbocation. So on the basis of analysis of the product, we can tell that this reaction follows this type of mechanism, where an intermediate of carbocation nature, they are formed in the reaction. Then another example, if we take toluene and we react this with chlorine, in the presence of light, the product formed is benzyl chloride. Whereas when the same reaction is done in presence of iron or iodine under reflex temperature, then we get a mixture of ortho and parachlorotoluenes. So in this case, the reaction is taking place at the side chain of the aromatic ring, whereas in this case the reaction is taking place on the aromatic ring. So this is an example of electrophilic aromatic substitution reaction, whereas this is an example of free radical reaction. So on the basis of the products formed under different conditions, we can tell that what kind of mechanism is involved in that type of reaction. So you can clearly see from here that how much the analysis of the product is important to finalize that what type of mechanism is involved in which type of reaction. Another example is parachlorotoluene. When this is reacted with sodamide, which is a strong base, in liquid ammonia as the solvent, then we will get these two products, paratoluene and metatoluene. Now if we think that this is a simply nucleophilic substitution reaction, that then the normal product would have been paratoluene only, that this chlorine is a chloride ion is a leaving group, and this is the nucleophile which will replace this chloride ion. So nucleophilic substitution will be involved, and if we see normally we should get only this product, but in addition to this we are getting metatoluene also. The formation of metatoluene indicates that this is not a simple nucleophilic substitution reaction. The intermediate, there is some intermediate involved, which is a symmetrical intermediate, and that intermediate can lead to the formation of two products when nucleophile will attack that intermediate. And when the reaction mechanism was studied, it was found that the intermediate involved in such type of reactions is benzene intermediate, which is a symmetrical intermediate, and now both the carbons at these places, they are symmetrical, so nucleophile can attack either this carbon or this carbon, and because of that, in this particular case, if we see, so this is one carbon, this is other carbon, and with the elimination of this we will get a symmetrical benzene intermediate, and then either nucleophile can attack this carbon or this carbon. If NH2 negative will attack this carbon, we will get this product. If it will attack this carbon, we will get meta product. So this is how the intermediate formed in this case can be enumerated on the basis of these two products which have been formed during the reaction. Then another example of product analysis leading to the mechanism of the reaction is Backman rearrangement. Now in Backman rearrangement, for example, if we take the case of acetophenone, when acetophenone is reacted with hydroxylamine, we will get two types of oximes. One oxime is this one, where this hydroxyl group is anti to the aromatic ring, whereas the second isomer of the oxime is where hydroxyl group is anti to the methyl group. And when this mixture of oximes is treated with phosphorus pentachloride, which is the condition under Backman rearrangement, we will get, in case of this oxime, we are getting this type of benzamide formed. N-methyl benzamide is formed where the methyl group migrates to the nitrogen. Whereas in this oxime, if we see, we get N-phenylethamide as the product. And if we see the mechanism here, the phenyl group has migrated to this nitrogen group of the oxime. So basically, on the basis of analysis of the products formed in both the cases, we can tell that it is always the group which is anti to the hydroxyl which will migrate during the Backman rearrangement. So identification of these products can tell us greater information about the mechanism of this reaction. So this anti-migration is also proved from these two examples. So if we are having 2-bromo-5-nitroacetophenone oxime where the hydroxyl group is anti to this methyl, whereas in this case the hydroxyl group is anti to this aromatic group. So when the reaction under Backman rearrangement was done with this, then the cyclized product was formed instead of migration instead of Backman rearrangement. Here the stereochemistry of the reactant is such that instead of undergoing Backman rearrangement, it undergoes cyclization at this aromatic ring with the removal of hydrogen from here and Br from here. HBr is eliminated and we get benzoxazoles as the product. Whereas in this case, this group is anti to this hydroxyl, and this undergoes Backman rearrangement to give us these types of amides as product with the migration of this aromatic ring to the nitrogen. So we can see that it is always anti-group with respect to hydroxyl of the oxime which migrates in case of Backman rearrangement. So the analysis of the products formed during these reactions gave us very useful information about the type of mechanism involved in various types of organic reactions. Then another example is the acid catalyzed rearrangement of these types of esters, ethyl beta phenyl beta methyl glycidate. So this is beta carbon beta methyl beta phenyl glycidate. So when this is reacted with Lewis acid BF3, we know that this will interact with the epoxide oxygen and we will get this type of intermediate where this carbon is having positive charge and this oxygen is having negative charge. So when this forms a carbon oxygen double bond, there is a possibility of migration of either this group or this group. So if hydride shift take place, then we will get this type of product, and if this ester group migrates, then we will get this type of aldehydic ester as the product. So when this reaction was performed, it was found that in actual this product is formed and this product is not formed. So this tells us from the analysis of the product that here the shifting of carb-ethoxy group takes place in preference to the hydride migration. So this group migrates in preference to hydride group, and that is why we are getting this as the product and this product is not formed. So this again is on the basis of analysis of the product formed, we can tell us that what type of intermediates they are involved and what is the mechanism of this reaction. The next is study of intermediates. So intermediates, they also give us very useful information about the mechanism of any type of reaction, and these intermediates they can either be isolated or they can be trapped, or they can be the formation of these intermediates, that can be studied through different spectroscopic techniques also. So some examples of actual isolation of intermediates involved in some reactions can be done. Then these can be detected by spectroscopic techniques, or they can be trapped by adding other types of compounds to give us stable products, which will give us useful information about the reaction mechanism. So one such reaction where the intermediates have actually been isolated is Backman rearrangement. So we know when amides they are reacted with under alkaline conditions, then these amides, they are converted into amines through this mechanism. In the first step, this proton from here is removed by the base, and we will get this type of intermediate, and this on reaction with one molecule of bromine will give us N-bromoamides as the intermediates, and these N-bromoamides, they will lead to the formation of isocyanates with the removal of water, and these isocyanates on hydrolysis will give us amines, and in this reaction these N-bromoamides and isocyanates, they have been actually isolated as intermediates during the formation of the product, and because of that we can tell exactly that how the different steps of this Backman rearrangement will take place, either through formation of N-bromoamide and isocyanate to give us primary amines as the products. Another example where the intermediates, they have been isolated is neighbor rearrangement. So neighbor rearrangement is tosylate oximes under basic conditions, they are converted into these types of beta amino ketones as the product, and here these types of azirenes, they are formed as intermediate, and in many neighbor rearrangement reactions these intermediates have actually been isolated during the reaction, and isolation of these intermediates proves that the mechanism of the reaction involved is like this. So in the first step, because this proton will be an acidic proton, this will be eliminated and we will get this type of carbanion, and this carbanion will attack this nitrogen with the elimination of tosylate group, which is a very easily removed leaving group, to give us these types of azirine intermediates, and then this hydroxyl group will attack this carbon which is more electropositive than the nitrogen, and more electrophilic carbon will be attacked by the base to give us these types of intermediates, and then this will abstract a proton, this nitrogen negative will abstract a proton from water, and we will get these types of intermediates which will undergo elimination of this proton, and a carbon oxygen double bond is generated, and this carbon nitrogen bond breaks to give us these types of products. Beta amino ketones, they are formed as the product. Then another example of intermediate formation is in case of these types of bimolecular aromatic nucleophilic substitution reactions. When these types of aromatic systems, they are reacted with nucleophile, then in the first step we will get these types of sigma complexes, and these sigma complexes then undergo elimination of this X group, which is a very fast step to give us these types of bimolecular aromatic nucleophilic substitution reaction products. And formation of these complexes has actually been achieved when this substrate is reacted with potassium methoxide, or this reactant is reacted with potassium methoxide. And you can see here the substitution is methoxy, whereas in this case the substitution is ethoxy. So this is treated with this, that means this will add to this carbon methoxy group, and when this will react with potassium ethoxide, then ethoxy will get added to this carbon, and we will get these types of sigma complexes. And these sigma complexes can only be formed if such type of mechanism is involved in the reaction. So these intermediates have actually been isolated during the reaction. And then another example of bimolecular aromatic electrophilic substitution is that instead of nucleophile, if we use electrophile, then these types of sigma complexes are formed, and these sigma complexes then will give us these types of electrophilic aromatic substitution products. And here also when these types of aromatic compounds, they are reacted with HF and BF3, then this will act, H positive will first act as the electrophile, which will add to the aromatic system, and we will get these types of sigma complexes which have actually been isolated at very low temperature of the order of minus 78 degree centigrade. Then in addition to isolation, these intermediates, they can be detected through various spectroscopic techniques like IR spectroscopy, UV spectroscopy, NMR spectroscopy, or ESR spectroscopy if the intermediate forms, they are paramagnetic in nature, that if there is a single electron present in that intermediate, we can detect those paramagnetic intermediates through ESR spectroscopy. And even flash photolysis has also been employed to study transient intermediates in solid, liquid, or gaseous state within the temperature range of common reagent. Then intermediacy of carbonium ions in unimolecular nucleophilic substitution reactions or unimolecular elimination reactions, that has also been established by NMR spectroscopy. So for example, if we take this substrate, this will undergo electrophilic aromatic substitution in presence of HF and BF3 negative. H positive will act as electrophile, will add to this carbon, and we will get this type of sigma complex. And if this complex is formed, which is an intermediate, then through NMR we can detect the presence of these two hydrogens at this carbon, and on the basis of that NMR we can tell that such type of intermediates they are formed during the reaction. So these are the examples of some use of NMR spectroscopy for detection of carbonium ions like isopropyl and tertiary amyl cations in the reactions. For example, if this tertiary butyl fluoride is reacted with SBF5 in liquid ammonia and NMR is taken for this, NMR for this substrate gives a signal for methyl as singlet for these 9 protons at chemical shift 1.3 delta. Whereas when this intermediate is formed, that elimination of this F creates a positive charge on this carbon, then the signal changes from 1.3 to 4.35. So when NMR was taken under these conditions, in actually the methyl groups they showed a peak at 4.35, which tells us that such type of intermediates they are formed during the reaction. Similarly, in case of isopropyl fluorides, they pass through these types of intermediates, and in the substrate, if we see the NMR spectrum, then methyl will show a peak at 1.23, whereas this proton will show a peak at 4.64 chemical shift delta. Whereas when these types of intermediates are formed, the signal for this methyl group shifts to delta 5.06, and signal for this goes to delta 13.05. So you can see the difference in change in the position of the signal for these group because of the formation of these types of intermediate. So detection of these intermediates gives us an insight into the mechanism of various types of nucleophilic substitution reactions or elimination reactions. Then similarly, third category is that the intermediate formed in these types of reactions, they can be trapped through different types of reactions. For example, we know when diazomethane is reacted under photochemical conditions, then these carbenes they are formed, they can be trapped with cyclohexene to give us these types of product. Similarly, nitrines they can be trapped by the aromatic systems to give us these types of azipenes. So if in some reaction nitrine is involved, we react with these, we will get these types of product which can tell us about the mechanism of the reaction. Then in these types of substrates, benzene is formed as the intermediate. We can prove the formation of this intermediate through reaction with anthracene, which will lead to the formation of these types of products. So if these types of products they are formed, then the existence of such type of intermediate is proved during the reaction. Either benzenes or nitrines or carbenes as intermediate is proved by the formation of these types of products. Then trapping of radicals in nitroso compounds can also be done, or activated alkenes can also be done by formation of different types of products. For example, if this alkene is involved in the bromination, this type of intermediate is formed. Formation of this intermediate is proved if we react with, this with different nucleophiles, and we will get these types of products correspondingly. And formation of these products can only arise if this type of intermediate is involved in the reaction. Similarly, in these types of nitroso compounds, the formation of these free radicals can be done through ESR spectroscopy also. And for example, aza isobutaronitrile on heating will give us these types of intermediates, and these will react with nitroso compounds to give us these types of stable products. And formation of these types of stable products can tell us about the mechanism of this reaction. So we will continue this lecture for the remaining methods for the determination of organic reaction mechanism. Thank you very much.